famous mathematician Benoit Mandelbrot proved that the smaller the unit of measurement that you use, the more accurate your final result. This is important to the work of Nasiim Harramain because he uses the Planck units, the smallest unit of measurement available in the universe, in his calculations, which leads to an unprecedented level of accuracy. So, how incredibly small is the Planck unit?
In order to give you a conceptual notion of the relationship in size between the Planck and the proton size, if the Planck was a little grain of sand, then the proton would be the size of the distance between the Earth and Alpha Centaurus, an enormous bubble that spans large amount of space, some 4 light years across.
And then fill it with grains of sand. That's how many Planck units are in the proton. Imagine every grain of sand on the Earth would just be the tiniest speck of the number of Planck units on a proton. Not only does this show how small the Planck unit is, but it also shows how many Planck units fit in a proton. Harramain calculated that all the little Planck pixels add up to all the information of all the other protons in the universe, and that the fluctuation of the Planck oscillators creates the information network that the universe uses to get constant feedback. Einstein was fascinated with light and how it worked. His famous thought experiments would lead to several counterintuitive ideas that would forever change our world. One of those ideas was his theory of relativity. Einstein's general theory of relativity explained gravity as a consequence of the curvature of space-time created by the presence of mass and energy, and that space-time could be calculated through geometry. It literally acts like a fabric that stretches and bends. When you put lighter objects near a heavier one, they spin in the gravity well created by the large object. Einstein saw the fabric of space-time and gravity as continuous. Harramain sees the fabric quantized with a sea of almost infinitely small Planck pixels. So it behaves like Einstein's fabric on a cosmological scale, but the big breakthrough is that because it is made of tiny quantized Planck pixels, it allows for the forces of spin and gravity to be accounted for by Harramain's geometry at the quantum level. If you think of the water in a perfectly still kitchen sink, it could look like a single sheet of water. But if you pull the drain, the water spins around the drain while the rest of the surface is perfectly flat. This is how Harramain's work gets results like Einstein's single sheet. Yet because the water is really tiny individual drops, it allows for spin to be present at the quantum level. The other difference is that we can't think of it as a single sheet. Think instead of it being stacked infinitely high and infinitely low, infinitely right and infinitely left, in a giant Planck pixel soup that fills the universe, allowing spin to occur anywhere.
Einstein geometrized space-time at the cosmological level, and until he died, he believed that there were gonna be a solution to do the same at the quantum level. So I was very much inspired by that.
As Einstein was fascinated by light, Harramain is relentlessly fascinated by the forces of spin.
Everything in the universe has spin. And I came to conclude eventually that the fundamental torque that produces the spin comes directly out of changes in density in the structure of space itself. Just like a little change in density between hot air and cold air produces a hurricane, which if you look carefully looks a lot like a galaxy. The same forces are generated in the structure of space itself because of a gradient or a change in the density of the energy of space. The structure of spin is critical to our understanding of the dynamics of the universe.
Think about all the ways we are spinning. The Earth spins at about 1,000 miles per hour at the equator. The Earth spins around the Sun at about 67,000 miles per hour. The Sun, with our solar system, is spinning around the galaxy at 515,000 miles per hour. The galaxy is moving through the universe at approximately 1.3 million miles per hour. Our DNA expresses spin. Atoms spin, protons spin, everything in the universe spins. Spin may be the one thing that connects us all. We are living in a universe where everything inside of it spins. Seeing the interconnection of all spinning things made Harrowmain look at gravity in a different way. Gravity is one of the most mysterious forces in the cosmos, which is why so few quantum models include gravity. This is part of the reason for the disconnect between the quantum world and the cosmological world. Harrowmain asked the question, where is the best place in the universe to observe the most intense interaction of the forces of spin and the force of gravity? The answer? The edge of a black hole. Harrowmain has studied the possible connection between the forces of spin and the forces of gravity being intertwined at a quantum level.
The spin dynamics of the structure of space-time itself is what produces what we call the black hole. And this new equation proves that. It proves that it's the Planck fluctuations that produces the effect. The black hole is actually the result of the little Planck's vacuum oscillations dynamically, collectively organizing